Hello everyone, welcome to my talk. The topic of my talk is the impact of sleep loss on attentional brain. Sleep is crucial for human survival and daily performance. As we can see from the figure on the left here, adults normally need 7 to 9 hours sleep per day. However, sleep loss commonly occurs in modern society. Individuals experience acute or chronic sleep deprivation due to working pressure, shift work, or sleep disorders. And insufficient sleep causes various dysfunctions of health and cognitive performance. Sleep loss can strongly impair various human cognitive functions, including attention, working memory, executive function, and decision-making. And in 2010, a meta-analysis by Lim and Dinges revealed that sleep loss strongly impaired people's simple attention compared with other cognitive functions. And subsequently, Ma conducted another meta-analysis with 11 fMRI studies of sleep deprivation on attention. The results demonstrated that reduced brain activation, including bilateral parietal lobe, insula, medial frontal gyrus, right precentral gyrus, and parahippocampal gyrus, while the increased activation was shown in the bilateral thalamus. And the finding in this meta-analysis uncovered the inconsistent evidence from the neuroimaging study, especially about the change of the thalamus after sleep deprivation, which is in line with the result from another review in 2017. One of the reasons for this inconsistency may be related with different cognitive tasks applied after sleep deprivation. And to further investigate the neural function after sleep deprivation, we try to use resting state fMRI, which without influence from behavioral tasks. The other aim of using resting state fMRI is to examine whether the magnitude of vigilance impairment after sleep deprivation can be predicted by the measures of spontaneous fluctuations and fluctuations and functional connectivity. In this study, we apply a within-participant design. 42 participants was recruited after both normal sleep and 24 hours sleep deprivation conditions, which were counterbalanced by participants and separated by at least 1 week. In the present study, we use a 10 minutes visual PVT task after the fMRI scanning to measure sustained attention under both well-rested and sleep deprivation state. The PVT task is widely used to measure sustained attention in sleep research because of its high reliability and high sensitivity to sleep loss. Participants were asked to focus their attention on a red rectangle box in the middle of the black screen, and monitor that the space for the appearance of a millisecond counter, which appeared at random interval ranging from 2 to 10 seconds. They were instructed to stop the counter as quickly as possible with a button press, after which they would be able to view their reaction time. If their reaction time longer than 500 milliseconds was defined as a lapse. As to the brain function, the amplitude of ALFF and functional connectivity was used to investigate the neurobiological change caused by sleep deprivation. In addition, correlation analysis was used to investigate the relationship between the change in ALFF and functional connectivity with vigilance performance. And here is the behavior result between the well-rested and the sleep deprivation states. As we can see, after sleep deprivation, the individual's attention was getting worse, which shown by more lapses and longer reaction time, as well as the higher sleepiness scores. For the result from the resting state fMRI significantly increased AFFF was shown in the region of the right paracentral lobe, bilateral thalamus, and the inferior orbital gyrus after sleep deprivation, while decreased ALFF was shown in the regions of the left middle frontal gyrus, right pericardius, right inferior parietal lobe, and right superior frontal gyrus. Here we observed the spontaneous function of the thalamus was increased after sleep deprivation. Since the thalamus is an essential node of the arousal system, increased AFF in the thalamus after sleep deprivation might represent a compensatory mechanism to maintain relative alertness. Based on the results of AFFF, we further analyzed the functional connectivity by using the regions that showed significant differences in AFF as seat regions, and calculate the association between the change of functional connectivity with PVT performance after sleep deprivation. Importantly, we found that the change of the functional connectivity between thalamus and bilateral frontal areas was negatively correlated with PVT performance decline. The disruption of thalamic connectivity with frontal regions might reflect microsleeps, which indicating instability of waking states. The findings from the resting state fMRI did give some further understanding on the neural change of the sleep deprivation, especially on the function of thalamus, but it still did not clearly answer the question about the functional change of thalamus after sleep loss. In 2017, Cross and colleagues proposed that the higher thalamic activity may sustain the reciprocal inhibition between the frontal parietal network and the default mode network, which means promoted the resistance to the impact of sleep pressure and maintain the normal vigilance performance. The lower thalamic activity may cause loss of the arousal signal from thalamus to the cerebral cortex, which confounded the FPN and the DMN anticorrelation and increased the possibility of lapses. To verify this hypothesis of the functional change of thalamus after sleep deprivation, we applied dynamic functional connectivity analysis on the task-based fMRI data and behavioral data during PVT in both sleep-rested and sleep-deprived states, and calculated the behavioral correlation between fluctuations in dynamic network connectivity with vigilance performance. 33 participants were recruited in this study, and they finished 2 counterbalanced sessions, 1 night of rested sleep and 1 night of total sleep deprivation. In this study, we applied dynamic functional connectivity analysis to investigate the temporal variability of thalamus after sleep deprivation. Dynamic functional connectivity analysis is a method with its unique advantage in capitalizing the time-varying moments of correlated both signal across the time scale of tens of seconds. Recent studies using DFC analysis discriminated 2 dynamic connectivity states, high arousal states and low arousal states. The functional connectivity pattern in specific period with higher spatial similarity to high arousal or low arousal DFC pattern was associated with faster or slower responses after sleep deprivation. From the results, we can see the proportion of high arousal states or low arousal states was positively or negatively correlated with reaction speed during temporal fluctuation. Compared with high arousal states, during low arousal states, decreased anti-correlation was shown between task-positive networks and default mode network. However, stronger anti-correlation was found between thalamus and the task-positive networks, as well as between thalamus and the default mode network. Furthermore, decreased anti-correlation between task-positive network and the default mode network was correlated with slower reaction speed. In addition, stronger negative functional connectivity in both task-positive network with thalamus and the default mode network with thalamus was shown. One individual performed slower under the lower arousal states. The present study examined the direct link between vigilance instability after sleep deprivation and functional connectivity in the thalamus with task-positive network and default mode network circuits. The findings reveal that one anti-correlation between task-related network and the default mode network was decreased. Individuals' reaction get worse. The thalamus modulates the anti-correlation between task-positive network and the default mode network. But after sleep deprivation, when the function of the thalamus is unstable, it could not modulate the functional connectivity between the task-positive network and the default mode network, which caused the reaction time getting worse after sleep loss. And we would like to thank the support from the National Natural Science Foundation of China and the Guangdong Basic and Applied Basic Research Foundation, and all the people from the Center for Sleep Research at the South China Normal University. And thank you for your attention, and I wish you have a good sleep every night.
Dear organizers and colleagues, I'm Qihong Zhou from Center for MRI Research, Peking University in China. It's my great honor to present at this symposium. My talk is about investigations of brain function during sleep and application to insomnia disorder based on EEG-IMRI. So sleep is a widespread biological phenomenon which is necessary for jellyfish, C. elegans, bees, whales, ducklings, giraffes, cats, monkeys, and for us. We spend about 1/3 of our lives during sleep, though universal. However, much is unknown about sleep. Recent progress has been achieved to understand the mechanisms and functions of sleep by applying multi-modality sleep neuroimaging techniques. Beyond EEG or PSG, the gold standard for sleep staging, multi-modality sleep neuroimaging platform includes MRI, MEG, PET-CT. So MRI could provide functional, structural, and metabolic measurements, while for MEG, it is quiet, provide measurements of neuronal activity, and with higher SNR compared to EEG, but much more expensive. PET could provide measurements of brain metabolites, including glucose, beta amyloid, and so on. For animal MRI, which could be very useful for translational studies from animal model to human beings. It should be noted that EEG is the only gold standard for sleep staging. All these neuroimaging techniques should be facilitated with simultaneous EEG equipment to investigate the sleep process. From the aspects of non-invasiveness, spatial and temporal resolution, fMRI and EEG has great advantages. Combination of EEG and fMRI could provide us powerful tool for macro-scale investigation of sleep functions and sleep mechanisms. So in the next, my talk will be presented from the following two aspects: the investigations of brain function during sleep using EEG-FMI and application of EEG-FMI techniques to insomnia disorder. So during a typical night's sleep, the brain moves through different physiological stages, including wakefulness, REM sleep, rapid eye movement, and non-REM sleep, including light sleep in stage N1 and N2, and deep sleep in stage N3. And they are presenting in repeating cycles. Each cycle takes about 90 minutes. So during EEG-IMRI scans, as the participants are instructed to lie still in a supine position, go to sleep in a very noisy environment. So it is very difficult to get whole night high quality sleep recordings. Thus, in most sleep EEG-IMRI studies, the researchers focus on the early portion or the late portion of the sleep, and mostly including the early portion, which includes wakefulness and non-REM sleep. Neuroimaging studies have consistently found a high level of brain activity occurs during resting wakefulness in the default mode network, which constitutes the posterior cingulate cortex precuneus, anterior cingulate cortex, and bilateral parietal lobule. This network has been served as a baseline of the brain and associated with mind-wandering, autobiographical memory, consciousness awareness, and so on. So by performing EEG-IMRI scan on 18 subjects after 44 hours of sleep deprivation, Horowitz and colleagues in NIH, they showed that distinct connectivity within the default mode network during wakefulness and deep sleep. Specifically, the anterior part, medial frontal cortex, and the posterior part of the default mode network was disconnected during deep sleep. Thus, they concluded that the DMN, the default mode network, may play an important role in the persistence of consciousness awareness, as when entering deep sleep, the consciousness faded. And for sleep, for human sleep or animal sleep, the most important function of sleep is clearance of waste products during wakefulness. The brain may clean out plaques during sleep. So let's see, using EEG-IMRI, what can we do? What can EEG-IMRI tell us about the clearance function during sleep? So this is a study conducted by Boston University, led by Fouts. They employed EEG fast fMRI techniques and scanned on participants when they go to sleep. They showed that during deep sleep, EEG slow waves, hemodynamic, and CSF oscillations are coherent and coupled. EEG slow waves are followed by hemodynamic oscillations, which are in turn coupled to CSF flow. These results demonstrated that the sleeping brain exhibits waves of CSF flow on a macroscopic scale, and these CSF dynamics are interlinked with neural and hemodynamic rhythms. As we know that arousal is a common event during sleep, arousal has been associated with several sleep disorders. The arousal, and the left panel shows a representative arousal during sleep by EEG. We can see that arousal is characterized by abrupt frequency changes in sleep, and generally an increase in amplitude in EMG. However, the brain regions associated with arousal is not clear yet. So in the current study, we collected EEG-IMRI data during the early portion of the sleep period. In healthy adults, arousals were identified based on EEG data after denoising. We can see similar arousal events during sleep, which is characterized by abrupt frequency changes in EEG and increase in amplitude in the EMG channel. After arousal identification based on EEG, the fMRI signals associated with arousals were analyzed with GLM model. So we can see subcortical regions, including the brainstem and the thalamus, were activated, while for cortical regions, including the temporal and occipital gyrus, were deactivated. So the activations associated with arousal in the subcortical regions is consistent with previous findings that subcortical regions are involved in behavior, arousal, and consciousness, while for cortical deactivations may serve as a mechanisms to direct incoming sensory stimuli to specific brain regions and monitor environment perturbations during sleep for sleep protection. And the hypothalamus is a crucial region for sleep regulation and wakefulness. There are several lines of evidence to support this notion, generated from animal studies. So firstly, the posterior hypothalamus is a member of the ascending arousal system that promotes wakefulness, while the anterior hypothalamus promotes sleep by sending inhibitory projections to the arousal system. Secondly, lesions in the posterior hypothalamus induce narcolepsy, while the lesion in the anterior one prevent patients from easily falling asleep. Lastly, the posterior and anterior hypothalamus have inversely related neural firing patterns and state-dependent. Recently, a new imaging study conducted under resting wakefulness condition. This suggested that the anterior and the posterior hypothalamus, one is for sleep promoting and one is for awake promoting. However, whether and how the functional networks of these two hypothalamic regions reorganize according to their wake and sleep promoting functions during sleep is not clear. So we constructed functional networks of the posterior hypothalamus and anterior hypothalamus during wakefulness and non-REM sleep, including stage 1, 2, and 3. As a result, from wakefulness to sleep, we observed decreased connectivity with the posterior hypothalamus decreased, and an increasing trend of functional connectivity with the anterior hypothalamus. All these results provide direct evidence that the correspondence between the network organizations and the hypothalamic sleep-wake regulation. According to recent neuroimaging studies, temporal fluctuation in functional connectivity patterns can be clustered into several states, and these states are corresponding to fluctuations to vigilance. We aim to investigate the characteristics and the electrophysiological arranging of these DFC, dynamic functional connectivity states, during wakefulness and sleep using EEG-IMRI. So we showed that during both wakefulness and sleep, the dynamic functional connectivity of the fMRI could be clustered into several states, and the DFC states consistently correspond to wakefulness and sleep stage, independent of the number of clusters. For example, when we set the number of clusters into 4, we can get 4 states. And for stage 1, this is closely related to wakefulness. And for stage 2, this is corresponding to deep sleep. Importantly, the mean dwell time of these DFC states are correlated to slow wave activity, and very important physiological marker for deep sleep. So we show that for stage 1, which is related to wakefulness, The mean dwell time of this state is negatively correlated with slow wave sleep power. And vice versa for state 2, which is closely related to deep sleep. So our findings suggest that possible electrophysiological source of these DFC states, which is corresponding to vigilance and corresponding to wakefulness and different stages of sleep. Next, I will share with you some results on the application of EEG-IMRI studies and applications to insomnia disorder. Insomnia disorder is the most common sleep disorder. Many studies have shown that hyperarousal plays a key role in the pathophysiology of insomnia, and hyperarousal is related to sleep misperception and sleep disturbances, which is the main clinical symptoms of insomnia. Here, we aim to elucidate the neuropathophysiology of insomnia disorder. We investigated the brain functional networks of patients and the healthy controls across the sleep-wake cycle using simultaneous EEG and fMRI using during wakefulness and sleep. And we chose a medial and anterior thalamic region as seed, considering its role in sleep-wake regulation in animal studies. As a result, we observed a significant group by stage interaction effect on the thalamic connectivity at widespread cortical regions. Importantly, the thalamic connectivity with a temporal region correlated with sleep misperception only in N1, the light sleep stage. That is, the more severe the patients underestimate their total sleep time, the lower the thalamic connectivity with this temporal region. As for the main effect of group, we showed that the insomnia patients exhibited lower thalamic connectivity towards the amygdala parahippocampal region in the subcortical area, and decreased connectivity across wakefulness and N1, N2, and N3 sleep. Similarly, we showed that the thalamic connectivity with this amygdala parahippocampal region associates with sleep misperception. Thus, our results show that this the thalamic connectivity with the temporal gyrus, with the subcortical, hippocampal, parahippocampal, and amygdala region is the functional brain basis for insomnia and is associated with misperception, which is a major clinical symptom for insomnia. And our results may provide potential therapeutic targets for insomnia. Beside arousal, we mentioned before, sleep spindles is another major characteristics during sleep. Sleep spindles have been implicated to show a major role in sleep protection and in emotion regulation. So we know that insomnia patients showed deficiency in sleep protection and in emotional regulation. So here we aim to investigate the relationship between spindle-related brain activation and these clinical symptoms in insomnia, using EEG-IMRI techniques during sleep on both insomnia patients and controls. So firstly, we showed that patients with insomnia showed significantly lower spindle numbers and lower spindle density. For spindle-related brain activations, we observed significant spindle activation in the frontal, temporal, and parietal for both groups. In addition, the healthy controls, the control subjects, showed additionally activations in the thalamus and cerebellum brainstem. For group comparisons, decreased bilateral spindle-related brain activation in the cingulate gyrus was observed. And moreover, this decreased cingulate spindle activation was associated with subjective sleep quality reflected by PSQI score and associated with emotional regulation reflected by self-rated anxiety score. So these results suggested that spindle-related activation in the cingulate gyrus are important neural marker for the subjective sleep quality and anxiety regulation for insomnia patients. I hope that I have convinced you that EEG-IMRI is a very powerful neuroimaging techniques that can be used to investigate brain mechanisms during sleep and can be applied to sleep disorders. However, analyzing the simultaneous EEG-IMRI data during sleep is extremely experience dependent and time consuming. So in our group, we developed a pipeline to automatically process and analyze EEG-IMRI data during sleep, namely APAS. So this pipeline could automatically pre-process fMRI data and get a whole set of fMRI indices. For EEG data, we used artificial intelligence in techniques for sleep staging, and also use an AI model to perform noise removal, especially the cardiac contamination. And we tested this pipeline on a very large EEG-IMRI sleep dataset on healthy adults. We showed that the accuracy for automatic sleep staging for EEG-IMRI data could achieve more than 70%. And the results based on AI sleep staging for fMRI data is very robust and reliable and comparable to that based on manual scoring and a combination of multiple softwares and processing platforms. So we have built a pipeline to automatic process EEG-IMRI data during sleep, which is efficient, reliable, and powerful. In the future, we need to put more efforts for events detection for EEG-IMRI data during sleep. So beyond EEG-IMRI data techniques at 3 Tesla, the next sleep neuroimaging platform could be extended to even higher magnetic fields, such as 7 Tesla. The good news is that simultaneous recording of EEG with 7 Tesla is feasible. And in Peking University, we also have designed a newer, higher SNR and more cost-effective MEG systems, which is with its advantages at 7 centimeter compact cylindrical shield, integrated audio-visual stimulation and adaptive scanning, helmet, and so on. So to conclude, EEG-IMRI techniques have shown its important role in revealing sleep mechanisms. And in the future, multi-center, large sample, and multi-modality neuroimaging datasets including both sleep-healthy populations and sleep disorder patients are needed. And application of deep learning methods are encouraged in future studies. Thank you for your attention. Any questions are welcomed.
Dear professors and colleagues, I am Zhang Jianhai from Hangzhou Dian University. I am honored to be invited to the 20th World Congress of Psychophysiology and glad to introduce our research work. This presentation focuses on EEG-based sleep staging analysis with functional connectivity. As we all know, sleep is an issue of great concern all over the world. A good sleep quality is related to our normal work and life. However, now more and more people are suffering from poor sleep quality, insomnia, and other sleep disorders. How to improve sleep quality has become an urgent and challenging research hotspot. Sleep staging is the basis of sleep quality evaluation and plays an important role in the early diagnosis and intervention of sleep disorders. At present, the method of clinical sleep staging is still mainly marketed by experts observing the brain waves during sleep. Obviously, this method is inefficient, time-consuming, and prone to subjective errors. So, finding an accurate automatic staging method is necessary. The most used sleep staging standard is established by the American Academy of Sleep Medicine, which divides the sleep stages into 5 stages: awake, rapid eye movement, N1, N2, and N3. In recent years, various physiological signals have been used in sleep analysis, including EEG, EMG, fMRI, even EOG. Among them, EEG is widely used in sleep staging research due to its advantages of low cost, high temporal resolution, and easy operation. Our work is also based on EEG signals. There are many types of EEG brain waves related to sleep, such as delta, alpha, sleep spindle, and so on. The types and spatial distributions of these waves are different for different sleep stages. For example, delta waves mainly appear in slow wave sleep. Spindle wave is an important waveform in sleep analysis. It appears in multiple sleep stages. For example, N2, S3, and S4. And the frequency varies in different sleep stages. In N2 stage, the frequency is about 12.5 to 15.5 Hz. In S3 stage, it's about 12 Hz and about 6 to 10 Hz in the S4 stage. So we think EEG frequency plays a key role in sleep stage analysis. For computational sleep staging research, the main objective is to find out discriminative features and good performing classification strategies. Recently, EEG-based sleep staging research has brought out many desirable results. Most of these studies obtain information from single channel. Use this information with feature engineering or directly use end-to-end deep learning models. These methods make good use of the local information of the brain, but it is difficult to exploit it from a global level. A brain functional network is a measurement for the information exchanging between brain regions. This work is to use brain functional connectivity to analyze the information interaction of different sleep stages from the global level. In our study, the dataset we used is the public sleep database from Sleep Disorder Center or the Orthopedia Major of Parma, including 4 healthy subjects. The data for each subject is about 7 to 9 hours, and there are 12 electrodes of bipolar traces. Because the state usually changes gradually and continuously, so it is very difficult to define clear boundaries between different sleep stages. To obtain accurately labeled samples, we delete the following 3 kinds of data. Okay, In pre-processing, we manually removed the data with obvious noise and used the common average reference to minimize the noise between each channel, and then for the removed ECG artifacts through ICA. Finally, we divided the EEG data into these 6 frequency bands, including low beta and high beta. For the construction of the brain functional network, the phase-locked value PRV is used. The PRV was proposed to measure the phase synchronization between 2 signals, which is only sensitive to phase but not to amplitude. Compared with other synchronization indicators, PRV is simple to operate and can maintain the same information level as other more complex indicators. In performing feature selection, we use the bi-sequence correlation coefficient to measure the ability of a feature to distinguish 2 classes. Here, the 2 classes specifically refer to the pairwise sleep stages. We perform feature selection mainly for feature frequency evaluation and analyze which frequency band features are more discriminative in sleep staging. Finally, support vector machines with the Gaussian kernel function was used as a classifier. After the frequency evaluation, we use the 3 information fusion methods to perform frequency band fusion. They are feature level fusion, decision level fusion, and hybrid fusion. Yeah, this is a schematic diagram of feature level and decision level operations. Hybrid fusion is to do feature level first, then decision level. Yeah, here I will give some results. Through PRV analysis, it's found that in some low frequency bands, such as delta and alpha bands, as the degree of sleep depends, the PRV value increases. On the contrary, in high frequency bands, such as high beta and gamma band, as the degree of sleep depends, PRV decreases. Looking at the distribution of PRV as a whole, from delta to gamma, the PRV of the 3 sleep stages are all downwards. But it is worth to note, while in the N3 state from theta frequency band to the alpha frequency band, PRV increases, showing a reverse trend. Some studies pay attention to the effect of alpha band in sleep. In our work, we also found the dominant role of the alpha band in sleep staging. As you can see, the distribution in the alpha band shows the maximum inter-class distance and a discriminative ratio in 3 classes. This has also been further verified in the subsequent classification accuracy results. Yeah, here are the classification results. Same as the above assumption, alpha does have the highest classification average accuracy, with a single frequency band reaching 90.986%. Then we compared the classification performance of different subjects, different frequency bands and multiple frequency band fusion strategies, and found that with the feature level fusion strategy and all the frequency bands used, the best classification performance is obtained is 96.14%. There are also some current studies exploring the role of beta wave in sleep, such as finding that beta activity is significantly increased in patients with insomnia, while reduced in patients with REM sleep disorders. In our work, we found the inconsistency between the low beta frequency band evaluation results and the sleep stage classification results. As you can see in this pie chart. About 30% and 27% of the top 95 and top 150 50 features with the best performance come from the low bit frequency band, which is only lower than the alpha frequency band. However, in the classification results, the results of low beta is almost the lowest in all frequency bands. Why so many features with high discrimination, but the classification result is not good? We found in the analysis of the discriminative ratio of the two stages of the frequency band, low beta has a high degree of discrimination between RAM and N2, RAM and N3, even the highest of all frequency bands. So in the feature selection, low beta is selected for so many features. But the combination of low beta between N2 and N3 stages is very low. So the classification accuracy of low bit frequency band is not good. But there is a special case. The accuracy rate of the low bit of the subject N10 reached about 92%. We checked the original data of subject N10 and found that N10 didn't have data in the S3 state. S3 is the boundary between N2 and N3. The lack of S3 data reduces the error scores of the N2 and N3 stages, so that accuracy of the subject N10 is relatively high, which also further verifies that the reason for the inconsistency of low beta and we discussed earlier. Yeah, this is the result of our comparison with state-of-art works. We reproduced other methods on the same data set. From the comparison, the average accuracy of our methods has certain advantages. Yeah. Here is our conclusions. It can be seen from the previous consent that the PRV-based brain function connection contains effective sleep stage information. As sleep depends, the average PRV increases in the delta and alpha band, while decreases in the high beta and gamma band during non-REM periods. Different frequency bands have different discriminative abilities for distinguishing between sleep stages. Alpha band shows the dominant role in sleep staging. Low bit shows good performance for classifying REM and N2 and REM and N3, but terrible for N2 and N3. The use of PRV-based brain function connection features can effectively distinguish different sleep stages. At the best average accuracy, about 96 was obtained. And that's all. Thanks for your listening. Thanks.
Hello everyone. Today I want to share our work about resting state EEG and its application. I'm from Sleep and Neuroimaging Center, Faculty of Psychology, Southwest University. I'm from Chongqing, China. I'm Xu Lei. So first of all, what is resting state EEG? Resting state EEG just record the eyes closed or eyes open conditions. EEG scope single, and it's simple in design. It only have a rest for 5 to 10 minutes and easy to follow. And it's suitable for children, older, or psychology disorder. And also, it has a large-scale database and very suitable to constructed large-scale database, such as HCP, ABCD, and it also have many open toolbooks, such as EEG Label, Lorita, SPM EEG. However, it has disadvantage. For example, it's heavily dependent on brain stage, vigilance, circadian rhythm, gender, age. All of these may influence this syndrome. And also there are many analysis methods. However, there are lack reproducibility tests. So here we want to test the reproducibility of the resting state EEG. First of all, we can compare the one person's in eyes closed condition, it's in the left side, and eyes open condition. You can find there are more than 16 channels recorded, and there are different in the 10 hertz. That was alpha rhythm. There are many other rhythms such as beta, theta, and delta, and each of them have different amplitude and reflected different brain stage. Also, we can find the eyes closed and eyes open in different subjects have very personal difference. For example, you can find for subject 4, it have very similar eyes closed and eyes open condition. However, for subject 73, the two conditions are very similar. So we want to maximum the difference between subjects, and also we want to smaller the difference between different tests. For example, for subject 4, each time we want to also have the similar spectrum for eyes closed condition. Also, resting state EEG, the larger is the alpha rhythm is changed from year to year. You can find it can reflect the maturational stage. For example, when a baby in 3 months, the largest power may 3 hertz, and this was increased when the subject is 12 years old, and it was very close to 10 hertz. Okay, so we can do resting state EEG analysis in time, space, and frequency. For frequency, you can find here the alpha rhythm is a frequency parameter, and it will have very old years for Hansberg recorded in his son's brain score. And also the space analysis usually based on the micro state EEG, and they find in fact the resting state EEG can separate to 4 EEG microstate. But here we discuss its source localization of the EEG record, and we have to many things in this field, both from time, space, and frequency. Here I introduced 2 of our work. First one is the reproducibility of power spectrum, functional collectivity, and network construction in resting state EEG. And another work is based on its application in insomnia disorder. Okay, first of all, what is the reliability and the validity? For the reliability, it's based on how focused of your test, and we can find the second row always have higher reliability. However, the validity is based on how many times it's touched the target. So you can find the third one have high reliability but low validity, and the fourth one have high reliability but high validity. And for the fMRI study, they have discussed the difference of brain state. And in this condition, they find only when eyes open and focused on fixation, the fMRI signal have highest reliability, and its default mode network have large activity. And also they find the reliability of fMRI signal is depend on the pre-process. And with the increase of the pre-process, they find the correlation is decreased. For in compare with EEG, there are many methods, there are many brain stage used, such as eyes open, eyes closed, eyes open with fixation, or changed from eyes open, eyes closed, each one with 10 seconds. So we want to compare the difference. Another thing we want to compare is that the 3 different parameters, that was power spectrum, collectivity, and the parameter of the complex network. Because all of the 3 network you can analysis in scope surface, also in the cortex. So we want to compare the difference between those 2 space. And also we want to compare the index of the collectivity, because there are some methods that was insensitive to volume conduction. Those methods such as phase lag index are insensitive to volume conduction. And we also want to discuss some recent developed methods such as the power envelope correlation, or PEC. And for network construction, we want to discuss the difference between dipole and ROI, because dipole usually have more than 10,000 dipole, but for ROI, for example, based on AAR or Brodmann, it's near about 100. So how to get the time course from dipole to ROI? There are, in fact, 4 methods based on the PCA, based on the center dipole, based on the mean of the ROI's center, or just simplify the forward model to only include the ROI region. So we have the following experiment design. We recruited the volunteer, and they have finished the general scale, and then they go to our lab 2 times. The first time they have tested the resting state EEG for eyes closed and eyes open, and then rest for 20 to 30 minutes, and then another resting state EEG record. And the second time is separated for 1 month, and they have the similar eyes closed and eyes open recording. We use the ICC to test the reliability. You can find that the ICC, if you want to have a large ICC to closed to 1, it must have very large inter-subject variability. With the same time, very small inter-test variability. So we want to compare the ICC between eyes open and eyes closed. We also want to discuss the difference between the relative power and absolute power. The relative power is based on the absolute power. However, the absolute power is only its original power, but the relative power used are just normalized the power and make sure the power have 100%. So it's have just normalized the inter-subject variability. For pre-process, we want to discuss the bad channel and bad echo, the process influence on ICC. We also used the ICA to delete the eyes-related defect. So here is our result. You can find for the first row, we compared the different rhythm in 4 conditions. in 4 conditions. Each panel have 4 conditions. The first 2 is related to eyes open, and the second 2 just related to eyes closed. You can find that eyes open are usually, for example, here for alpha 1, usually smaller than eyes closed. And another interesting thing is that in the same eyes closed condition, you can find if you use the absolutely power, you can greatly increase the when you use the relatively power. That was the first cluster. And for each one, this is the influence of pre-process. With the increase of the pre-process, the reliability can be increased. We also compared the different lengths of EEG signal. We can find with the increase of the time course, for example, from 4 seconds to 200 seconds, it will have greatly increased the reliability. Our result is that we find the eyes open is usually smaller than eyes closed condition. Another interesting result is that the relatively power here is larger than absolutely power, both for eyes closed and eyes open. And with more pre-processed state, this reliability can be increased. Interesting is here, you can find in the eyes open condition, the relative power have greatly processed if you use the ICA. And we also find that with increased time recording, this reliability can increase. However, for eyes closed, when the recording is longer than 30 seconds, it have very stable, even with increased recording. So we also find the reliability of different cortex. We find the visual and the parietal cortex have very large reliability for ICC. And we compared the different condition. We have different surface, and the top surface related to eyes closed, and the bottom surface eyes open, and the left surface for cortex, right surface for the scope, and the rear surface for the relative power, and the distance surface for the absolute power. We can find the power spectrum have largest reliability when used relatively power and in the eyes closed condition and in the scope surface. Also, we can find the similar condition for functional correctivity. However, here our closed and distance surface is related to sensitive to volume conduction or insensitive to volume conduction. We can find sensitive to volume conduction has larger reliability. Recently, we have developed our software to resting state EEG analysis toolbox. This toolbox, you can have process one button, but you have the scope power spectrum, scope correctivity, scope complex the network, and also you can find the result of the cortex level. In the cortex level, this work we have prepared, and we will just open access for this toolbox. So here we introduced our another work in resting state EEG in insomnia disorder. It was a meta-analysis. We find, in fact, recently there are many analyses use the resting state EEG, and for example, for 10 different disorder, they have different find. Some, for example, for delta, some have find there is no difference, and there are 3 work find there are increased in delta, and some find there are just opposing result. So for this result, we want to discuss about how the result of insomnia. And after we have discussed about the work, we find in fact for insomnia, for the long REM sleep, stage 1, stage 2, stage 3, we always find that there is increased of power spectrum in insomnia in nearly all of the frequency band. And another interesting thing is in waking condition, because for waking condition, you only need to record for 5 minutes, but you can find there are very similar results when compared with whole night recording. So we have the following assumption that for the insomnia in resting state spectrum, there is a 4-band power increase, and there are all-day increase. That even in you are awake, in resting state awake, you also can find there is ubiquital cortical hyperarousal. So we have following the Prisma meta-analysis method, and we have find more than 1,000 work related about this topic. However, after we analysis, we find there are only 30 work related to the wakefulness, and 17 work related to the long REM sleep, and the 5 work related to REM sleep. And after the analysis, we find the absolute power and relative power may influence our result. So we just combine both of them. You can find here for weak condition, the alpha reason is very different for absolute power, but for relative power, it has a low difference. And for the long REM stage, the alpha power is significantly different for relatively parameter, but it has a low difference in the absolute power. So we combine both of the relatively and absolutely method, and also the waking condition and the sleep condition, and we have make sure the 4-band power increase and all days increase. And here we want to introduce the toolbox of the resting state EEG. In fact, we find that many work is based on power spectrum. In fact, it's only one method for resting state EEG. You also can use the sleep stage classification or some micro-state EEG analysis. For example, source localization, time frequency analysis, scope-free analysis, cross-band coping. And those methods we find it's a rare discussed in this field. And the resting state weak condition may be a very good choice when you cannot have a long whole night record of EEG. So our conclusion, the resting state EEG has the advantage of the non-invasive, simple, and easy to operate. It has great potential in the study of the neural mechanism in psychology, neuroscience, and psychopathology. And the retest reliability is that eyes closed have larger reliability than in open eyes condition. So we must pay attention to the removal of the artifact of the eyes-related electric activity. And the relative power have larger absolute power. It may be the importance of the measurement normalization. And the application insomnia we find the increase of the energy in all frequency band. So both states of sleep and wakefulness are manifested as ubiquital cortical hyperarousal, and resting state EEG play an important role in diagnosis, treatment, and prognosis. So thank you for your attention, and we all